we're going to look at solving limits through algebraic techniques. And if you are a random person on the internet and you want to print a sheet to follow along, you can go to this bit.ly link, bit.ly/capital ALG, capital LIMITS. All right, moving on. So let's look at this. So some techniques for solving limits algebraically. So this is when you have the equation of your function, and we're going to try to solve with algebra. Your first step is to simply do direct substitution. So if x is approaching 4, you plug 4 in for the x's, and that will work only if your function is continuous at that x coordinate in question. If your function is discontinuous, then substitution will not work. Most of the time, direct substitution fails. There's our bell. Direct substitution will fail because it gives you an indeterminate form. And the indeterminate form, we will see the overwhelming majority of the time is 0 divided by 0. However, there is another one that is infinity divided by infinity, and there are actually several more indeterminate forms. We're going to focus on these two, and really we're going to focus on the 0 over 0 for now. And if you do get those, that just means we have to do some more work. Now, eventually in calculus, you will learn of a technique called L'Hopital's rule that we can use in these indeterminate forms. This video or this lesson does not include L'Hopital's rule. We will get to that later. We will usually have 0 divided by 0. That was supposed to be a green pen. And if you do get 0 divided by 0, the more work, the extra work you are going to do, you are ultimately trying to find something to cancel. So I'm going to add that in the margin here. So if you get 0 divided by 0, that means we will apply algebra until I can cancel something on top and on bottom. And after that canceling step, you go back to direct substitution, and it will usually work at that point. So in order to cancel something, we could factor and cancel. So if you have polynomials that are factorable, that is an option. You can also, in the case of polynomials, do long or synthetic division. Sometimes a synthetic division is just easier than trying to factor, or you could do long division. You could also try to rationalize either the numerator or denominator. If you happen to see a square root, that would be an option. And if you cannot factor and cancel or you cannot rationalize, I have this generic catch-all down here, which I'm just going to call other algebra. So that could be expanding binomials. It could be using a common denominator trick that we'll get to in a little bit. So you're ultimately trying to find something that will cancel in the 0 divided by 0 case. And once you get to the canceling step, you go back to direct substitution. So let's give this a shot. And there's a typo on this one. This is supposed to be a 5, not a 3. So I'm going to change that. So that is now a 5. And if x is approaching 3, I'm going to start by just substituting 3 for the x. We'll have 5 times 3 minus 7. And then we'll take all of that and raise that to the 2/3 power. 5 times 3 is 15 minus 7. That's 8 to the 2/3. You should be able to do this without a calculator. If I have a rational exponent like that, I like to focus on the denominator of that exponent first. So I'm going to do the cubed root of 8, and then I will square that. And that ultimately is 4. So there's your answer for number 1. You just substitute it. And if you get a nice number, then you get a nice number. But that doesn't happen very often. So let's look at this one. If x is approaching 3, I'm going to start by substituting the 3. 3 squared is 9. 8 times 3 is 24 plus 15 over 3 minus 3. And you can very quickly tell that the denominator is going to be 0, yet you still want to substitute in the numerator as well, because if it's not a 0 on top, that actually means something different. But we do end up getting that 0 divided by 0 indeterminate form. And I actually have kind of angered the gods of math here, because I shouldn't write equals 0 over 0. A limit can't equal 0 over 0. So that's a little bit of an error. Really, what I probably should have done is just said that like this is approaching 0 and this is approaching 0. So we do have zeros on top and bottom. Just a little picky thing. In either case, that does mean that I need to do some more work, and this one will factor. And if you have a really hard time factoring in the context of limits that are in indeterminate form, you can kind of cheat a little bit, because I know I need to cancel that x minus 3. So there must be an x minus 3 when you factor the numerator. And there is, because this numerator will factor to x minus 3, x minus 5. At that point, I can cancel the x minus 3's, divide them out. And now I can substitute again. I'll try my substitution. Now it's only x minus 5. So I plug in 3 for the x, and 3 minus 5 is -2. So there's our answer for number 2. Let's look at this one. X approaches -2 of this one, and if I substitute again, I have -2 squared is 4 minus 4. So that numerator is approaching 0. Negative 2 cubed is negative 8 plus 8. The denominator is also approaching 0. And so we would try to factor this one. So I'm going to do limit as x approaches negative 2. The numerator is a difference of squares. So that's x plus 2, x minus 2. The denominator is a sum of cubes, which does factor. I'm going to write the formula up here. So if you have something cubed, and actually you can factor a sum or a difference of cubes, and it factors to this. So I'm going to write the formula for you, and then it's a squared. You change the sign on the second one, ab plus b squared. And so there's your formula. If you start with a plus between them, then you keep the top sign. If you start with a minus between them, then you keep the bottom sign. And the way I keep the signs straight is your first sign is always the same that you start with. The second sign is always the opposite. And the third sign is always positive. So you would use SOAP to keep the signs straight. As far as the individual terms, AB, A squared, AB, and B squared, that you're just kind of on your own, whatever you can do to get that. So this one will factor. Back to this problem, that'll be x plus 2. So your a would be the x, because x is being cubed to the cube root of 8 is 2. So b is 2. So it's a plus b, then a squared. Change the sign, a times b, which will be 2x plus b squared will be 4. Now I can cancel the x plus 2's. And when I substitute again, negative 2 minus 2 is negative 4. Negative 2 squared is 4. Negative 2 times negative 2 is positive 4 plus 4. That's a lot of 4's. And that ultimately reduces to negative 1/3. There's our answer for 3. Onward we go. Let's look at 4. So this one we actually have 2 options, but I see a square root in the denominator. If you go through the substitution step, 4 minus 4 is indeed 0. Square root of 4 minus 2 is also 0. So we need to do some extra work. And this one, I see a square root in the denominator. So I'm actually going to rationalize the denominator by multiplying by the conjugate of that radical expression. And I'll do that on top and bottom. And in limits, we will only expand the conjugate pairs. Do not expand that numerator. I'm going to leave that numerator as x minus 4 root x plus 2. The denominator, we're going to expand that. And the beauty of conjugates is you don't have to do a full expansion. I only need to multiply root x times root x, which is x, and negative 2 times positive 2, which is negative 4. And now I can see that these x minus 4's will divide out, and I can substitute the 4 in for the x. So we end up with the square root of 4 plus 2, which is 4. So there's that one. Now I'm going to work this one out a second time just to give you another option. And so what you could do is you could actually factor the numerator in this one. So I'm looking at the denominator, that's root x minus 2. The top, I'm going to do what I call force factoring, and I'm going to change x minus 4 into the square root of x squared minus 4. And now that looks an awful lot like the expression a squared minus 4, which is a difference of squares, a plus 2, a minus 2, except my a term is the square root of x. So that numerator is actually going to factor to the square root of x plus 2 and the square root of x minus 2 over the square root of x minus 2, and we will apply the limit to this. And now I can cancel the square root of x minus 2's. I can plug 4 in for that, so I get the square root of x, which is the square root of 4, plus 2, and we get the exact same answer we had just a minute ago. Okay, so let's talk a little bit about how you write your answers when you are solving limits. So how to appropriately show work when solving limits. What you do not want to do is this. Now we may look at this and go ahead and tell, okay, 5 squared minus 25 is 0. 5 squared minus 6 times 5 plus 5 is also 0. So I can tell this is indeterminate. I'm going to have to do some more work. And so that more work is to factor. So I'm going to factor the top, x plus 5, x minus 5. I'm going to factor the bottom, which would be x minus 1, x minus 5. That's not a 5. And then I can cancel these x minus 5's. And after canceling, I can substitute my x approaches 5. So 5 plus 5 over 5 minus 1, which is 10 divided by 4, which would reduce to 5 halves. Okay, so that is indeed the correct answer. The answer is 5 halves. However, if this were a free response question on the AP exam, you would lose points because you committed a sin. We actually call it a linkage error. It is inappropriate use of the equals sign, because what I did is I lost my operator. It's not the rational expression. It's not x plus 5, x minus 5 over x minus 1 times x minus 5. It's not this that is equal to 5 halves. It's the limit of that is equal to 5 halves. And when I lost that limit operator, I have now made an inappropriate linkage with those equals. So the best way I can explain this to get it to make a little bit more sense to you is if I were to give you the question, let's go back to like Algebra 1, the square root of 4 times 5 plus 5, and you said, okay, well, 4 times 5 is 20, plus 5 is 25, and then the square root of 25 is 5. So I ended up with the right answer. The square root, the final answer should be 5. However, in the end, I incorrectly said that 25 is equal to 5. That is not a true statement. And so what I would need to do to correct this is I would have to actually keep that square root operator until you actually find the square root of the argument, and that gives me the answer of 5. So same thing here. When you're doing limits, you want to definitely keep writing the limit as x approaches 5 until you actually substitute. So right now, I only need to add that one limit because it is the limit of this that is equal to 5 plus 5 or 5 minus 1. And now I have correctly written my work for that example. So just keep that in mind. I'm very picky about your math grammar. It's not only about getting the answers, it's about having appropriate work. So I'm going to do a few more examples here. I think I have 3 more. So I have the square root of x plus 1 minus 2. So if I plug in 3, that'll be square root of 4 minus 2. Okay, that top is approaching 0. 3 minus 3, that is also 0. So I'm actually going to rationalize this. I see a square root, and I'm going to multiply the top and the bottom by the conjugate of that numerator, which you keep the same 2 terms. You keep the radical term and the constant. You just change the sign between them. And again, remember, you only expand the conjugate pairs. I will not expand the denominator. So that's x minus 3 and the quantity x plus 1 plus 2. And when you multiply out conjugates, we only need to focus on the first times the first and the last times the last. That's what conjugates do. So root x plus 1 times root x plus 1 is x plus 1. Negative 2 times positive 2 is negative 4. And when you combine that numerator, we end up with x minus 3, which is beautiful because I have an x minus 3 in the denominator as well. Plus 2. Keep the limit. I have not substituted yet. So I keep writing limit as x approaches 3. I will cancel those. Since my numerator has disappeared, I'll stick a 1 up there to hold its place. And when I substitute 3 for all remaining x's, I end up with 1 over the square root of 3 plus 1. Square root of 3 plus 1, that'd be square root of 4 plus 2. And my answer is 1/4. So there we go. I think I have 2 more. 6 and 7, yes. All right, so 6. H approaches 0. Now pay attention. This is H approaching 0, not X approaching 0. So I'm going to substitute 0 for the H's. And if I do that, I'll have X plus 0 squared. So X squared minus X squared will approach 0. If I plug in 0 for that H, my denominator is approaching 0 as well. So this is indeterminate. I need to do some work until something cancels. It's actually possible to factor the numerator as a difference of squares. However, I am not going to do that. In this case, I'm actually going to fully expand the numerator. So if I square x plus h, I'll end up with x squared plus 2xh plus h squared minus x squared. And then my denominator is h squared. And if you look at that numerator, now my x squared minus x squared subtracts out. And of the 2 remaining terms, I can factor an h out. So I'll have h. Why do I write an h squared down there? That should just be an h. Whoops. So I factor an h out of the numerator, which leaves me with 2x plus h. The denominator is also an h. And I told you a long time ago, in the indeterminate form, 0 divided by 0, you're going to apply algebra until you can cancel something. And I now can cancel those h's. And once I cancel those h's, I'm back to the direct substitution step, and we get 2x plus 0, which if you remember your plus 0 tables, the answer is just 2x. And it is okay to have an answer with x's in it. As far as the limit's concerned, x is kind of a constant. H is the variable that we are substituting in. So there's our answer to 6. And then I'm going to knock out 7. And I'm going to show you a trick to 7. It's kind of ugly. We have 1 over x minus 1/3 over x minus 3. If I substitute 3 in for the x's, I do get 0 in the numerator and 0 in the denominator. And one option for this one, and I'm not going to do this, but one option is to ignore everything except those two fractions in the numerator. And we can actually get a common denominator in the numerator and combine those two things into a single fraction. And then you can divide and simplify the division of those two terms. But I'm going to show you another trick. What I like to do is I like to look at every term in this fraction. I have a 1 over x, a 1 over 3. Technically, this is x over 1 and x over 3. And I find the common denominator for all four, for everything in the expression, and my common denominator would be 3 times x. So I'm going to multiply 3x through the numerator and through the denominator. And when I do that, it gets very nice. So when I distribute that 3x through here, and actually, I'm only going to multiply the 3x through the numerator. I'm not going to distribute the 3x through the denominator. When I do that, I have 1 over x times 3x is just 3. Minus, then I have 1/3 times 3x is just x. So I have 3 minus x over x minus 3 times 3x. And I told you when you get 0 divided by 0, you should do some work until a factor cancels, and we're almost there. We are almost there. 3 minus x and x minus 3, they can cancel, but they are opposites. So when you cancel those, there should be a -1 somewhere. The easiest way to see that would be to factor a -1 out of that numerator. And if you do that, -1 times x would be -x. -1 times -3 would be a +3. And now I can cancel x minus 3's. And I can substitute now 0, 0. X is approaching 3, not 0. Whoops. So I'm going to plug in 3 for my 1 remaining x. I have a -1 up there in the numerator, and I have 3 times 3 in the denominator. And so the answer is indeed -1/9. That was a weird 9 there. That's still weird, but at least you can read it. There we go. Those are all the examples for solving limits algebraically. Hopefully that makes a little bit of sense to you.